we gotta do. All right, so I'll finish up the chapter 11, but let's do a little bit of a review. Okay, so maybe we can just make sure. Okay, so here's one thing. This is a kind of a practice you can try. This is what we already did before. So, okay. Can you guys do this one real quick? Okay. So this is what we did before, and okay. You can think about the SN2. SN2 reaction. Okay, about 1 minute. Okay. I tried to hold another review on Monday, so we'll have enough time for the reviewing chapters. But I'll just make sure you guys keep watching the review sessions for exam 1 and 2, because I only have a time for reviewing chapter 10 and 11. So yeah. Okay, so think about it. So this is what we did for SN2. Okay, as you remember, if you look at the living group trend. This is very poor living group. Okay? Hydrox group is really poor living group. So to substitute this group, you need to do that with some special agent we call diachloride. They form better living groups. Okay, and then one chlorine break apart, and they do it here. So if you think about the SN2, SN2 is happening at the same time. So you're gonna have the nucleophile attacking, and the leaving group is about to leave. So they will show you transition state. Do you guys remember this? Okay. So because of the transition state they need to go through, this will be only attached to the opposite side of the leaving group. Because the leaving group is still there. This is still there, right? So it can't replace the way it is already there. How can it replace the one that is already there? They need to leave so they can replace, right? So they're coming on the back. Okay. So whenever you do this one here, okay, just copy everything else. But this will leave, right? The Hydrox will leave, and you need to put chlorine on the back. So it'll be dashed. Okay, makes sense, right? Let's just try one more. This is also what we did on Wednesday. I'll show you this same. Change the phosphorus triangle. Yeah. Try this one, maybe 1 minute. So from today, I'll try to be very practical for the findings. But the final exam will be comprehensive, there won't be many questions from chapter 10 and 11. Okay, so it's pretty much the same. They're gonna form better living group like this, and then there's one bromine anion will be there, and this is also SN2. So then this will bound to in this position. Because it was before you had a Hydrox bond from the front, but when it bound on the back, it has to be on the back side, so it'll be this. Makes sense, right? I think, yeah. Okay. Let's do this one more. This is also what we did on Wednesday. Try the. So now you have a pretty good living group now. Okay. Sodium, think about the same mechanism. Okay, so so this is quite easy now, but you need to think about which one is your nucleophile? Because obviously sodium cannot be nucleophile because it's a metal. They tend to be positive charged when they ionize. So the other one is anion, which you guys remember, if a nucleophile is effective for SN2, if it's negative charge, it's a stronger nucleophile. Okay, so this is the one that is good nucleophile, but it will also going onto the back. So not just replacing the bromo groups, but there will be substitute on the back, like this. Makes sense, right? I think. So after this, we talked about the SN1, and this is the example I showed you before. Okay, so maybe. Okay, so here's the thing. I told you. I totally understand. It's so hard to distinguish the SN1, SN2, SN1. Later we gonna kick up the elimination too. But for this one, most of the time, when you look at the solvent, it tells you almost everything. So if you look at the solvent, if it's either water or ethanol or mixture, you can almost assume 90% chance it will be just SN1. So this will be SN1. And also, if you think about one more thing, if you look at this carbon right now, here, this is a tertiary. Tertiary is very slow in SN2. You guys remember this, right? Because the SN2 has to come on the back, right? Because this is the leaving group that will form the transition state. But it's really bulky on the other side. Then the nucleophile can come into the back because it's too crowded here. So if it's tertiary, SN2 is almost impossible. It may be possible, but very slow. So it is almost certain by looking at the carbonated tertiary in ethanol, it gotta be SN1, not 2. Okay? Makes sense, right? Okay. Can you guys try this one real quick? Just 1 minute. So remember, SN1, you're gonna have 2 products, okay? Not just one. Because you're gonna have a carbocation intermediate. I actually forgot one more thing. So for SN1, when you look at the nucleophile, it's neutral, right? It's not negatively charged. For SN1, it doesn't really matter when it's negative charge or neutral. It does matter in SN2 because you don't have a leaving group there. Remember that, right? With the carbocation. So it doesn't really matter in SN1. So this is a very good example of SN1. This carbonate tertiary. Your solvent is very protic solvent, and also it's bulky, and the nucleophile is not so strong. So it won't be good for SN2 anyway. Okay. So you're gonna have a 2. Oops. Okay. And then you're gonna have another one, right? That goes to the inversions, not just the retention of a stereochemistry. You're gonna have this one too. 2 products over here. So as I mentioned before, this will be 50-50 chance because this water only bonds when it's formed carbocation. So this will be on the same plane. They open to the left and the right on both sides. Okay? But like I told you before, still the retention is harder. because when the leaving group leaves, the nucleophile almost immediately bond to the carbon almost right after. So because of the very slight, like a small interaction, when with the leaving groups with the new nucleophile, it has a little bit of a less favor on the keeping the retention of the stoichiometry, but still it'll be more easier, slightly easier for them to on the back still. But still, there will be two parts. Kind of makes sense, right? Does it make sense? All right. This the thing. Okay, looks good. Right. Okay. Okay, so maybe I'll give you more practical problems as a review. Okay. So maybe you can try this one. Okay. Yeah, try to predict this one. And focus on this one. This is what it looks like. It's a sodium acid. This is what it looks like. So this will be your So you maybe can say, oh, this gotta be this direction, just by looking at this one. And I promise you, I'm not gonna trick with this one, solvent. So this is one hint I can give you for the final exam. So if you just look at the solvent, it will be just that. They have some tricky one. I won't do it on the final. Okay, so what happens is this one. So can you guys guess it could be SN1 or SN2?
SN1.
SN1, perfect. This is SN1, right? SN1. And then think about it. This group is in the sort of a secondary position and also benzylic position. Okay, so this will be very good chance that we'll have one SN1. Okay. So in this case, this nucleophile will be replaced by this one. So you're gonna have this one, right? And then what? Second will be this. Okay, two product will be there. Makes sense, right? Make sense?
So what's the product? Is it
This one. Okay, I'll show you. So you're gonna draw the two product. This is SN1, right? Retention and inversion. So just copy the same thing. I'm kind of trying to avoid this area because there's the light on it. So anyway, just copy the same thing over here, and there's one that is looks like this. Okay, this is a wedge. Okay, there's another one has dash. This one. One, two. Okay, so this is wedge, or this is nucleophilic attack. This is on the back, dash line. Two. This is SM1. Okay. Okay. And this will be slightly minor because it's a retention. This will be slightly more free-flow as a major because it's a inversion. Okay. But almost same. Almost. Okay. Makes sense, right? So the one trick you can do is just look at the solvent. If it's water or ethanol, it will be 90% chance SN. Okay. Does it make sense? You're so quiet. Okay, so let's try one more. So, okay, so once again, I'm not gonna lie. If you look at the solvent, you can just do it. Okay. There's some tricky one. I won't do it. Okay. So maybe you can try this one. Okay. With the same nuclear file. Okay. But your solvent is DMF. Dimethylformamide. So this is a polar aprotic, so they are not able to do hydrogen. So what this might be. And think about this one. This carbon is primary. Okay, look at this one. This carbon is primary, and this is polar aprotic solvent. What reaction that will be? Okay, so yeah, so just keep everything same. You should need to know what happened to you when you had a living group, right? There were 1, 2, and then here you just need to put this one. Okay, because this will be this one, so it goes to here, which is easy because it's only primary. And this is DMF, so it'll be SN2 range. Okay, so the funny thing here is though that you don't have to show me the stereochemistry on this carbon. Can you guys guess why? Because I just didn't show you the wet or dash line over here. I just replaced them. Okay, can you guys guess why? Because this is not stereocenter. There's 2 hydrogen on it, so it's not chiral center. So you just need to replace it. It's even easier, right? So look at the solvent, which is good for SN2, because it's a polar aprotic. They don't have a hydrogen bond in the solvent, and this is a primary, so it's easier for them to attack on the back. So it's very SN2 typical reaction. Okay. Makes sense, right? Okay. Good. All right. So far. So yeah, I'll keep saying for your final, just look at the solvent. We'll almost tell you everything. Okay. I'm not gonna trick or anything. So so can you guys try this one too? This is what we did on Wednesday as well. Okay, this one real quick. So you just need to think about the Dice rule. Spell right? Oh, sorry. It's Dice. So this is elimination. I'll give you about 1 minute. This is what we did on Wednesday. I think this is what we did on Wednesday. Okay, so here what you need to think of is that there will be two products, but there will be major and minor. You can think of that one because you have a hydrogen over here, or either you can have a hydrogen on the terminal position here. But what we prefer on this what? Okay. That's interesting. So you have this one here, which is will be your major, and you're going to have this one as minor. So this is major, this is major, this is minor. Okay. So this is major, this is minor because of the how much your substitute your alkane is. So if they taking the hydrogen in the inner carbons, they're going to take the hydrogen, so they goes to here, so they form the double bond here. And as that, the leaving group will just leave like this. So that's how you can have alkene form when the base comes in, grab the hydrogen, the pair electron goes to the two carbons, and that push will make the leaving group to leave. Okay? So that's why you have a part over here. And the other one is they can drop on the different position of the hydrogen. So they can form, grab this one, and it goes to here and goes to leave. Okay? So you have a two possible scenario which happens, but this will be major because this is a more substitute. So if you look at this one here, it's R, hydrogen, hydrogen, and this is the hydrogen, 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 and just only one R. So as you remember from the previous chapter, if the double bond is more substitute with the R groups, it will be more stable that way. So that's why you're gonna have this compound as your major product, and the other way is minor product is less stable because it's less substitute on the double. Okay. Okay, let's do one more. This is also what we did on Wednesday. Yeah, let's try to do this one real quick. Yeah, same thing. So try to find the most substitute major alkene possible products as your major product, and then the other one would be the minor because it will be less substitute than the other. Okay? It's the same rule that we're gonna apply for this one as well. Okay, so you guys got it right. So you have this one. Okay. You can have this one. So it depends on which hydrogen will pick up your nucleophile. Either you're coming from here, just there, either coming from here or there. Okay. But as you know, this will be only di-substitute, but this is tri-substitute. So this is kind of a reason why this will be your major. This will be.
Which one's major and minor?
Oh, so if you look at the two possible products, depends on which hydrogen were taken by the nucleophile. You have those two carbons. So you have two carbons in the double bond, and you just need to count the. So this is actually what it looks like. Okay, this is actually what it looks like, because this is actually. So this is actually what it looks like, right? You guys know that, right? Okay. So they just pick one of this and goes there, and this is gone. That's this one, okay? And then you can pick one of this one, which is here. So when this pick up one of this one, and those goes to there. So it'll be done, and this will be gone. This one. Okay. So it depends on which hydrogen taken by nucleophile. They have two products, but this will be major because if you look at these two carbons surrounded by three carbons, three R groups. This is only two. This is only, so these two carbon, this is only one, two. This di-substitute, this is tri-substitute. So tri-substitute is more stable alkene than di-substitute alkene. Was it chapter 6, I believe? Yeah. Chapter 7, I'm not sure. So anyway, does it make sense? Okay. Yeah. So hopefully by now, when you look at the skeleton structure, try to remember the implied hydrogens and everything will help you to predict the product. Okay. So I'm gonna just finish up with some types of the elimination today, and then I'm gonna hold another review on Monday. Okay. So we'll have some more time to think about it. So we have a SM1. I'm sorry. Now we're gonna talk about the elimination now. So elimination, we have E1. So E1 is normally happen with SM1 together. So normally they work together, okay? So, but what it does is very similar to SM1, okay? SM1 is, so in SM1, you need to have a carbocation intermediate first, okay? So whenever you have a carbons over here, okay? Some R groups over here. What it does is they actually leave first, like it did in SM1. So they form carbocation, because the leaving group will leave first. Okay? So this is almost same as SM1. And then the base, or you can say the nucleophile, just grabs it. So whatever so it doesn't have to be actual base. It behaves like a, okay. Anyway, so this one grabs it and then goes there. So it's also two-step. Oh, I'm sorry. This is it depends on the two steps. So this is the late determining groups there. So this will be now become alkene, and just this will be gone. So if it works it this way, it's an E1 elimination, which is very similar to SM1. But the only difference is now they're just taking the hydrogen, they what? Substitute the way it was leaving group. That's the only difference between these two. Okay, makes sense, right? Okay. So what about we have a E2? Okay, so E2 can happen independently. Sometimes it happens with the SM2 together. But E2 can be independently happen sometimes. Certain conditions, I guess. Okay, so this is also pretty much the same as same mechanism you saw in the SN2. So SN2, it happens in almost simultaneously, right? The leaving group leave, and then your nucleophile going to the tap on the back. But in this case, they're gonna tap on the hydrogen, not the position of the way you have leaving groups. So they're not coming on the back, but they're coming onto the anti-periplanar position. So this is the maybe base. So in this case, E2, your nucleophile will be most likely actual base, like a literal base, like OH minus sort of thing. Okay? And then they goes to there, same happening almost at the same time, like SN2. Only difference is SN2 is coming on this side, just by replacing it. But E2 is coming onto the hydrogen to make the double bond, to make that leave. So it also happened same time. So we call this E2 because it's very similar to the SN2. Okay. Makes sense, right? Okay. Good. So the last one is E1CB. I'm not gonna do this on the final exam, to be honest. But what it does is, whenever you have a leaving groups, the base comes and grabs this one first, but it not goes on to the here first. It stays on the carbon for in one step. So this will actually form carbanium, carbon anion, carbanium. Okay, so it's a negative charge because it's a 1, 2, 3, 4, 5. Okay, and then later it goes to there, and they leave. So they form here. So unlike the one we did for E1, E1 is forming what? Carbocation, right? In E1CB, it actually forms carbanium. Okay, so I'm not going to do this on the final exam because it's not so common because it has a certain conditions to make it happen. For example, if we have this one over here, okay, this one picked up by base, this will be anion, and then it stays there. The push on the neighboring carbon, not goes to there automatically, and it pushes up this one here, become negative charge, and pushes back on here. It's the carbonyl groups again, and it pushes back onto the here. So there's electric push, and then they leave. It's because of this carbonyl groups has a special function. Do you see this carbon with the oxygen, which is electronegative, in double bond? We call this carbonyl groups. But when you do that, because this is an electron rich now, right? This is the electron rich in this carbon, but this is electron poor because it has a very strong bond to the electronegative element, which is oxygen. So they tend to go to this one first. And then they, with sequential movement, they make enough push to make the double bond here so they can leave. Okay. Yeah. All right, so I'll just finish here today. Let's do extra.